I wanted to bring into everyone's attention because I think it's so very important. So it's one of these rare occasions where theory really can drive practice and can, for me as an applied statistician, I think this is one of the most important developments that I've been able to witness over the last 5 years. So this is evidenced by the very long list of prestigious publications that this work has come out in, and so I think that the majority of the work that we're hearing is from the NeurIPS paper, but Pat has now got an industry in generating NeurIPS and other GladRag papers, including RSSB and other top tier stats places. So it's very exciting. I'll let the speakers tell you why. Okay, so Annie, please take it away.
Thanks very much. I'm just going to share my screen. Can everyone see that all right?
Yep, it's now full screen. Brilliant. Cool. Thank you very much.
Hi. Yeah, so thank you, Dan and Tamara and Kate and JGI and Heilbronn for putting this on and inviting for us to talk. Me and Patrick are going to be giving a little talk about the statistical task of graph embedding. So kind of representing nodes in a network as points in space to be able to use that point cloud for other data analysis, for example, like clustering or anomaly detection. So this is kind of part of a larger research program with contributions from all of the people here. So I'm going to start off with kind of giving a hopefully motivating application for this work, and then pass over to Patrick to go into more of the details of how you actually do it. So kind of as an ongoing collaboration with Microsoft, we've been looking at using some of the techniques we've developed to detect patterns of corruption. We've been looking at data from Brazil because they have some really amazing open source government data. They have loads of it out there if anyone needs some good data. And one source of corruption that we've been looking at is the procurement process. So that's how government award contracts for stuff like public goods and services. So for example, like a government could need a school to be built, and they need to give out different parts of that to different companies to build. So they might have one company that's just doing the building. They might have other companies supplying equipment for in the school. But that process kind of is quite ripe for corruption in kind of different ways. Governments can try and take advantage of this process, and government officials can collude with companies to kind of make more money for themselves, or companies themselves can just try and inflate prices of things and generally make money. So this data set has about 435,000 companies across kind of 35 time points, where a time point is about a quarter of a year. And our aim is to kind of create this network by connecting companies by things they have in common. So that could relate to different parts of the actual contract. So the buyer, who's kind of like who funds the project, or they're involved in the same contract themselves. So they could be involved in different parts of the same overall project. They could have the same items, so they work in similar industries, or they could have probably what you would consider as more like concrete relationships. So they could have the same contact details, or they could be part of the same like parent company, or have the same partners. So partners are just kind of the people that own these companies. And so within this data set, there is 26 million edges, but we also have access to some different red flags, things you would probably consider quite suspicious. So something quite concrete, like having a company that's just been punished, like suspended or fined for doing something illegal, or you have these companies that have entered like leniency agreements. So that's when a company kind of admits they've done wrong, they've been caught out, and they admit it, and it means they can carry on operating, but they've just had to pay a fine or something. Or you have other things like partners of companies can be government officials, which is obviously not great. So the kind of aim is to work out how do companies like inherent risk from other people, like how does my operation in connection to other companies expose me to risk, and how can we just detect general patterns of corruption. So we have like this network of companies where each node is a company, and here we can see that some of these nodes are colored black. That indicates that this company has had a red flag against it. So if you were looking at quite a small network like this one, you could probably just kind of see which companies you'd be interested in looking at. So like, for example, this company has 3 connections to companies with red flags. You'd probably be quite interested in it. But you can imagine that as that gets bigger and you get way more companies, almost 500,000, that gets very complicated quite quickly. And some of the methods of corruption can get quite complex, like these ownership structures. So we kind of want to represent these companies as points in space. And first we do that by creating a matrix out of this network. So we create this matrix where the element ij is a 1 if these companies have a connection, and then it's a 0 otherwise. So this allows us to do a graph embedding of the network. I'm not going to really go into how you do that right now. I'm going to leave that to Patrick, but I'm going to trust that you believe me that we can represent these companies as points in space. And it allows us to position them so that companies that are close to each other are considered similar. So they might have a lot of connections with each other, and they produce, this data produces quite a cool looking structure where currently the colors indicate that they're the same company, but I would probably ignore those because quite a lot of the shapes are quite similar, so it's quite hard to tell them apart. But what this kind of allows us to do is diffuse risk from one company to the other based on distance. So you could measure companies' exposure to different risk from other companies. So for example, if in this little structure here there was a company that had a red flag, you'd probably want the companies near it to kind of get some of that risk from them. But kind of without having red flags, we can just look at general patterns of corruption and how we could find those in the embedded space. So I'm going to kind of describe a couple of methods and how that behavior would look in the embedding, so what we would look for. So to start with, we have a thing called bid rigging, which is where multiple companies will bid for the same contracts often to try and artificially inflate the price of them. And kind of often those companies will be owned by the same people, but they'll be posing as different companies to make it look like a fair bidding process, but it's kind of fixed. And kind of what you'd expect to see in the embedding in that kind of scenario is that these companies would all be close to each other and they would appear in the same time points. And then the other kind of side of that is what we have is company reinvention. So this is when one company kind of needs to rebrand for some reason. They probably caught doing something they shouldn't have. And so they have to stop operating, but they obviously don't want to. So what they do is they go away and they change their name and maybe some other things about them. And then they just come back and kind of carry on doing what they were doing before. And kind of for that example, you'd expect these companies to be close to each other, but they actually don't appear in the same time points. So we'd be trying to find companies that are close, but aren't in the same time points. Ooh. But like there's quite a few different issues you could think about here. Like the main one probably is different kinds of relationships. You would probably say companies are more similar to each other based on which relationships they share. So if we think back to earlier, if 2 companies were working in the same field, that's not really that much of an indicator if one is corrupt that the other one probably would be. But for example, if 2 companies shared the same like email address or phone number, that would probably more likely imply that they might be the same company, and you would consider that a more important relationship. So we need to think about how we deal with those kinds of relationships, and should they all be treated the same? Similarly, when we looked at the risk, there's probably different areas of risk that are probably considered more risky than others. And then the other big issue that we have is there's a temporal aspect to this data. So we want to be able to look at how companies change over time and how their position is changing over time, and how that changes with respect to other people. So how do we deal with that temporal aspect so that we can compare over time points? I'm going to pass over to Patrick to try and answer some of these questions and tell you a bit more about graph embedding.
Okay, is this, can everyone see and hear me? Great. Thanks a lot, Annie, and let me also echo Annie in thanking Dan, Tamara, the JGI, and the Heilbronn Institute for Mathematical Research for putting this event on. So I'm going to spend not more than 20 minutes trying to tell you a little bit more about the methods, the theory, and even it's fair to say perhaps the concepts that we've developed over the last few years that help us tackle an application like the one that Annie described. So after I'm done, Annie will take over again and just briefly just tell you the latest discovery we made, and that this is the time when suddenly maybe things will get a little bit more theoretical, but I'm going to try to keep it to a sort of highlight overview level and only just mention maybe the theoretical highlights and their methodological implications. So graph embedding, right, to put it a little bit more formally than Annie, but obviously not super formally, it's just a diagram. What we're basically imagining is that we have a graph. So this is what we consider to be the data, right? So we observe that thing. And so I've drawn one here on 6 nodes. And when we embed a graph, right, we're trying to find, we're trying to represent each node of a graph as a point in space. Right? So if you're trying to visualize a graph, then probably you'll be using 2-dimensional space, right? So you'll be picking p equals 2. But for almost any actual interesting inferential task that isn't visualization, probably you're going to pick p a little bit higher, or even maybe much higher. Okay, so we're looking for a potentially high-dimensional representation of the nodes of a graph. Now, this is a topic which, for several reasons, has really boomed in statistics, machine learning, AI, and data science, right? And it's not really for me to say exactly why it has, right? But reasons that are often given are, well, one of them is just the internet, right? The internet somehow seems to be creating a lot of networks, right? And I think the other realization that a lot of people are having is that many modern data sets, either explicitly or to some level implicitly, actually take the form of a graph, right? So it just seems like a good structure to try to understand a bit better. But obviously, because the application of graph embedding is so pervasive and just occurs in so many different areas, it's studied by a lot of people for very different applications, in very different sort of, according to very different scientific traditions. And that's a very good thing, you know, overwhelmingly so. But obviously one consequence is that there's perhaps quite a lot of confusion surrounding this whole area, right? And there are questions in particular that I think as a group we have been confused about for a number of years, right? And I sort of thought I would settle on these 4 questions, right? Should a link somehow in a network be interpreted as a similarity? If you have a binary data matrix, right, something that represents, for example, connections between users and items, I mean, is that what we mean by a graph, right? Is that analyzable by our methods, right? As Annie alluded to, a problem that seems to be bothering a lot of people is somehow how you incorporate time into the analysis, right? Because almost every network we actually encounter in the real world seems to have some sort of time dimension, right? We talk about dynamic networks. So how can you do graph embedding in a sensible way when nodes are somehow changing over time? And then, you know, if you're a statistician, I mean, is graph embedding just dimension reduction? You know, is it just a fancy form of dimension reduction? I'm not necessarily going to explicitly give you my answer to these questions, right? But I think at the end of a talk, in my talk and at the end of Annie's talk, it should hopefully be clear what we feel is the answer to each of these questions. So, graph embedding, there's a million different ways of doing it. We use a million different ways. I'm just going to focus for the purpose of this presentation on the one we understand best at a theoretical level, right? And that's graph spectral embedding. And if you're not mathematically minded, the details don't really matter. But if you are, then what you're going to do is you're going to look at the spectrum of A, so all of its eigenvalues, and you're going to somehow find an elbow, right? And there are automatic ways of picking that elbow. So this is a place where the spectrum looks like it's sort of ending, and then the rest are just kind of indistinguishable from zero somehow. And you're going to pick out that bulk, right? Those non-zero eigenvalues, those p non-zero eigenvalues, and you're going to work out what's called the rank P spectral decomposition of A. Right? So you pick out the P principal eigenvectors, the corresponding P principal eigenvalues, and then construct this matrix X hat, right, which is going to be n by P, and it's going to contain in each row a P-dimensional representation of a corresponding node. Okay, so that's a way of doing graph embedding. It's not a very good way if you've got a big graph, and in practice, what we always do is the thing that's underneath, and it's just that the theory is a little bit more complicated. But of course, there are many other ways. At one point, I'll show you the result of node-to-vec, for example. Okay, so this is graph spectral embedding applied to a light-hearted and even perhaps quite childish example. Right, so this is a graph of Harry Potter characters, right? So there are something like 51 main characters in the Harry Potter series, and you're going to put a link between two characters if they're enemies. Okay. So if you work out the scree plot, so that's the first plot. That's the plot of a singular values, and you ask any method to tell you how many of these singular values are, distinguishable from zero. Your answer typically is 2. These 2 values here sort of stand out somehow. So what we're going to want to do here is embed into 2 dimensions. Okay. Now the corresponding eigenvalues, they're the singular values, but they're signed, so they can be positive or negative. We see that there's one large positive eigenvalue here, and this slightly smaller value over here is represented as a very small negative eigenvalue down here. Okay, so we're going to take this Harry Potter graph, we're going to embed it into 2 dimensions. Okay. So this is what you get, right? So these are all the characters. I'm hoping, of course, that a lot of you are familiar with the story. What you see basically is these 2 sort of rays. And if you're familiar enough with the story and you look carefully enough, you'll notice that these rays basically distinguish the good characters from the bad characters, right? So you've got Harry Potter over here, and you've got Voldemort all the way down here, right? And if you look at other parts in the picture, you'll sort of see good people all the way down here, and how far up or down the ray you are is basically how many enemies you have, right? So Harry Potter and Lord Voldemort are like the antagonist and the protagonist of the story. So they have more enemies, and that's why they're far out in this picture. Okay. Now, it's a childish example, of course, but it should hopefully challenge some of your assumptions already, because if we believe there are somehow 2 clusters here, right, the good guys and the bad guys, it's clear, right, that a link between 2 characters is not an evidence of similarity, right? You have a link if you're enemies. You don't have a link if you're friends, right? So clearly, in a graph like that, there's going to be a real problem if you're using a graph embedding technique which somehow interprets a link to somehow be a form of similarity, right? And so, perhaps a really critical message that I want to put forward is it's a kind of a crucial mistake to assume that the links in the graph are necessarily evidence of actual similarity between the 2 nodes involved. And it's a critical mistake that you could easily make, because, for example, you could easily use node-to-vec, which is, I believe, the most popular graph embedding technique. And if you do use node-to-vec on this data, this sort of intrinsic assumption that a link means similarity will cause this embedding to occur, right? And it's, it's obviously inferior, right? So it really is something you perhaps have to be careful of in real graphs. And you might say, well, okay, hang on. You might say, well, okay, that seemed like a bit of a contrived example. Well, in my best attempt at a real world graph survey, where I just picked an arbitrary graph from any number, a very large number of different domains that I could find online. We do basically find what you're looking at here is the last column here, the number of negative eigenvalues among the principal eigenvalues selected in each of these graphs. And we do basically find that almost half the time, actually exactly half the time as it happens, we do have important negative components. So there's a sense, at least, in which similarity in each of these graphs is actually inversely related to propensity to connect. I had an example given to me once of a perfect example, I thought, of why you might have this sort of mixed homophilic and heterophilic effect, and the good example I thought was football rivalry, right? If you imagine what it takes for two football teams to be rivals, they might easily be very close in terms of physical distance, right? Like Glasgow, Celtic and Rangers, but in the abstract space of political and religious beliefs, they're probably very distant. Right? So there are some dimensions in which similarity would be sort of proportional to the probability of connecting, and other dimensions in which similarity would be inversely proportional. Okay, so I think this is the most theoretical slide I have, and it's just a very quick summary of what we know about graph embedded positions, right, under spectral embedding. So it takes a lot of work to actually define some notion of true latent positions, x1 and xn, so just take that as given. What our theory says basically is two pretty important things, right? The first one is that somehow the graph embedded positions, these x hat I, are uniformly consistent, right? So as the graph gets large, each estimate gets closer to the truth, and not only that, but the maximum error across the whole node set is shrinking to 0 in probability. That's an extremely powerful result, as I'm sure you can imagine, for any sort of follow-on geometric analysis or machine learning task. And the other result we have is that the errors asymptotically are Gaussian, are normal, right? Now, you'll notice that what I've said isn't exactly what I've written. There's a matrix Q here that you need to somehow align the estimates with the true positions. And that matrix Q basically reflects the fact that you can't know the positions up to more than some sort of rotation, right? So you need to apply some sort of global rotation before you can hope to have this sort of perfect alignment. But once you know that, once an oracle gives you that rotation, you have very, very strong results about how good your graph embedding is when your graph is large. Okay. So, for a lot of problems that I'm sure a lot of you have encountered in the real world, what you actually notice is that you don't have a simple undirected graph, right? You have something that's a little bit more complex than a simple undirected graph. And the usual way that's the case is because your graph is what we call multipartite, right? You've actually got a graph that's kind of like people connecting to different places, or you have Tesco, the Tesco club card system where you have customers and linking to certain products that they buy, and you have users and computers. That's a cybersecurity application. But of course, the situation can be more complex, right? You can have drugs, diseases, genes, and other stuff. You can have buyers, tenders, and items. That's the anti-corruption application Annie alluded to. In cybersecurity, you could have users, computers, processes, and you can have these kind of graphs that connect all of these objects of different types, right? And we call them bipartite graphs. So there's just two types, and multipartite graphs that are more than two types. And the question you might ask is, well, is any of this relevant to these sorts of graphs, right? Which are probably the graphs that you actually encounter most often. And the answer is yes. You can just think of those as graphs. But it helps to know that they're multipartite graphs, because if you know that they're multipartite and you know which objects are of which type, what you'll actually find is that the embedded positions live in quite a high dimensional space, but the objects of the same type are all going to live in a low dimensional subspace, right? And you can apply PCA basically, as shown, as illustrated to you in right-hand figure, you can apply PCA to each of these separate point clouds, and you know that you know how to separate them because you know what objects type each object is. And by applying PCA, you get this much finer and lower dimensional representation of the nodes, right? That you can hope to have much better inferential power with. Okay, and this is one of the things, of course, we had to use for the anti-corruption application, because we have companies, we have buyers, we have tenders, and they're all sort of interconnected in these ways. So what we do is we globally embed them and then apply PCA. Okay. So the next thing that you might be worried about is this temporal dimension, right? So your graph might be evolving over time. You've got the same nodes, but you observe their links, and their links might actually change over time. So for this example, we have this another toy data set, basically. It involves school children in France. And the graph basically is created by physical connections, basically. So when two students come close, they're both wearing lanyards or something, and that basically gives a signal that they've come close, right? And so what you have as a result is this evolving graph, which just shows the proximity of different students over time. And it's a lovely data example. I mean, for many reasons, it's kind of cute, but also because we know which actual classroom each of the students belong to, and so we can hope to rediscover that in the data, right? And we'd like to know how the patterns of interaction might change over time for various reasons. So here, I suppose what you want if you're doing graph embedding is you want some vector representation of each pupil, but for that vector representation to evolve over time in a meaningful way, right, to reflect their behavior. So we won't have time to go into immense detail here, but we've basically come up with this idea of using the unfolding, basically, of graph adjacency matrices, right? So what you do is you take each of the graph snapshots, so the graph at time 1 all the way to the graph at time t, you just literally column concatenate them, and you spectrally embed that in the same way that we spectrally embedded a single graph before. This is going to give you these time-varying representations of each of the nodes, and you might hope, mightn't you, that was somehow sensible. Well, we discovered last year that, to our best knowledge, this is the only way, or it's the first algorithm at least, to provide an embedding that is consistent in a way that is useful for most tasks that we kind of imagine you might want to use an embedding for, right? So in particular, it's spatially consistent. So if you've got two nodes that are behaving, two nodes that are behaving in the same sort of way at a point in time, then they'll be embedded to the same position up to noise. And similarly, if you've got a single node and it's not changing its behavior over time, then that node will be embedded to the same position over time, right? So you've got this temporal consistency and the spatial consistency. And I think that's what you probably want if you're trying to get a dynamic graph embedding, right? We discovered first that unfolded spectral embedding did that, and also that it was the only method at the time that could do that. So to give you an illustration on this primary school data, what you've got here is the embedding over time. So it looks a little bit, each snapshot looks a little bit like the Harry Potter graph, right? And there's a reason why. And you see that there's some sort of stability, right? So the green point cloud is roughly in the same position over time, right? Except at lunchtime, right? And what happens basically is the students all mingle, right? And the teachers here, who are represented in black, they stay far away from the pupils. This happens again at lunchtime here on day 1, and then the students all go back into their classrooms before mingling again on day 2 at lunchtime. Right? And there's a funny story actually of why here you have some apparent separation between certain classes and other classes. It's to do with how large the cafeteria was. So that's what you get if you use unfolded spectral embedding. If you do the naive thing, which is just embed each snapshot independently, and you look at what you get, well, it's, clearly you've got no temporal stability here. And if you use a very honorable rival, omnibus spectral embedding, so this is something that came slightly before our method, you have the opposite, basically. You have this temporal stability, so it's very nice, but what you don't have is the spatial stability. So in particular here at lunchtime, you have a problem where basically these clusters here, they're completely made up. They're phantom clusters are inherited from other time points. Okay, a very quick motivation for the final part of the talk, which Annie is going to go into in much more interesting detail, which is perhaps one whole new and exciting branch of methodology that was kind of opened by some pretty heuristic and dodgy data analyses that I sort of conducted a few years ago. But I would say in my defense that this is basically what a lot of people have been doing, and it has been working. It's just that for a long time we had no idea why, right? And this is a point that when you have a large graph, it seems to turn out to be useful to graph embed into a very large dimension, and then use some sort of modern visualization technique like UMAP or TSNE to get a picture in low dimensions. Right. And when you do that, you get these kind of stunning pictures of graphs, which are meaningful. So for example, here you've got consumers and restaurants, and I've colored the restaurants here by the US state that they're in, right? So the colors are, they're independent information that kind of indicates that the structure you're looking at here isn't completely made up. And so there seemed to be this emerging realization that although we might like to embed it to quite a high dimension, the structure might actually be much lower dimensional, right? And if you apply various intrinsic dimension estimation tools, they're literally sort of hundreds, I just picked a few, then you do sort of get that even though this point cloud is secretly in a very high dimension, the estimated true dimension of a point cloud is something more like between 3 and 4. Okay. And so I got thinking a few years ago, like, is there an explanation why somehow graph embeddings would need to be much larger, would be in quite a high dimension, and yet yet the points in that high dimension might only live in some lower dimensional space. And I'll give you the best I could achieve at the time, which was one theorem, which basically kind of shows that should just about be true, right? So if your graph is somehow driven by low dimensional structure, right? So if there are true positions, Z1 up to Zn, which are quite low dimensional, but then there's some function f, which is generating the edges, but just takes two of these low dimensional positions and just returns the probability that the two nodes should connect. And you don't know what that function is, and it could be quite complicated. Well, if you just assume that it's sufficiently smooth, what you're actually going to find is that when you embed, you need to pick quite a high dimension, technically even an infinite dimension. But in fact, those positions are actually going to live very close to a much lower dimensional set, technically in the sense of a Hausdorff dimension. Right? So just as a very brief example, if you simulate a bunch of graphs which come from latent position models where the true positions are actually just real values, so they're just one number, right? But the kernel f, which is giving you the probability of two of these positions actually generating a connection. This kernel could be anything, could be quite a complicated function here, or something I've specifically picked to be pathological, or this Gaussian radial basis kernel. Then indeed, if you simulate a graph from that and you spectrally embed it, then what you get is these very high dimensional pictures. Of course, I'm just showing you 3 dimensions, but you see that somehow the embedding concentrates about a much lower dimensional structure. And that's basically all I had at the time. So that's it for me. And I think I'm passing back on to Annie now.
Annie, we can't hear you.
Thanks. So yeah, I'm going to start off by giving an algorithm as kind of a solution, and then I'm going to go back and explain why you should do that. So we start off with that latent position model, and we have these kind of 2 steps. And the first one is that matrix factorization step. So that's the graph embedding step, and it means you obtain this high dimensional embedding where they live close to that low dimensional kind of manifold. And then what you should do next is a dimension reduction technique. So there are quite a few out there for both of those things, but I'm going to talk about two that are mathematically tractable, but I think later I'll give a bit of experimental evidence of kind of some other combinations that you could use. So to go back, the first bit is you do the matrix factorization, which was described earlier, the spectral embedding. And so then the second step, isomap, what it aims to do is it takes these high dimensional points and it makes a neighborhood graph out of them. So it makes this graph where two nodes are connected if they're kind of within this radius epsilon of each other. And what you want to do is trying to make that epsilon as small as possible while keeping everything connected still. And then what it does is it calculates all of the shortest paths within that neighborhood graph. So you're kind of finding the shortest paths that kind of respect the manifold, kind of along the manifold. So in this figure here, you can see between xi hat and xj hat, it's kind of finding this kind of approximate distance along the manifold. And it gives you this matrix of shortest path lengths. And then once you have a matrix of these shortest paths, you can apply classic multidimensional scaling to what we propose are some good estimates for your ZIs and ZJs. But I will go on to tell you why you should do that. But I'm going to have to set up a bit of theory first. So we kind of have three assumptions I'm going to talk about. The first one just allows us to define the manifold. So we have this Z, which is like the domain in which the latent positions are valued. And then we also have the F. Our kernel is a Mercer kernel, so we can write it as inner product of a feature map. And that allows us to define the manifold as the image of the Zs by the feature map of the kernel. So just another little diagram is that you have the Zs and you can transform them by the phi to have points along the manifold, which we know earlier that we can use spectral embedding to approximate these positions and approximate them quite well. Our second assumption is an assumption that means that phi is injective, so that each point on the manifold has a unique pre-image. So going back, that you can reverse phi. And then we have this second assumption here that's kind of, it's that this matrix H is a positive definite matrix, and it kind of ensures that the relationship between our Z and our M is non-degenerate, and it allows us to talk about the geometry of those two spaces. So the main theorem of this paper that me, Patrick, and Nick wrote together was about path lengths in this space and how they relate to the distances in your latent space. So if we're assuming these three assumptions, then we can talk about the path in M and how it relates to its corresponding path in Z. And that's given by this equation here, but kind of in more accessible terms, what we're saying is that the geodesic distance between 2 points, 5zi and 5zj in M, so that's minimizing this left-hand side, that geodesic distance is going to be equal to the distance between their pre-images with respect to some Riemannian metric, which we need to specify through the matrix H that I talked about earlier. So why using isomap is effective is that it's approximating these geodesic distances, which allows you to then just use a classic multiple dimensional scaling to approximate your Zs. And kind of even more interestingly, we found that for some families of kernels, we can actually find what this relationship is in a closed form. So if I just focus on the first one, so when your kernel is a function of Euclidean distance between your two inputs, if we have that our domain is convex and there's a local maximum at 0, then what we end up having is that actually those two distances are just proportional to each other. So your distances along that manifold, your geodesic distances, will just be proportional to the distances in Z. And we kind of have these other quite similarly simple relationships. And these kind of tell us that calculating the geodesic distances along the manifold will help us to recover the distances between the corresponding points kind of up to some simple transformation. And then importantly, once you've got those distances, you can propose estimates for your Zs. And I've kind of got a couple of examples. The first one is it's a simulated data example that just is kind of proof of concept more than anything else. So we've kind of chosen our latent positions so that we can show the recovery of them. So we've chosen points on a grid, so just a two-dimensional grid, deterministic points equally spaced, so that we can increase the number and see how that affects it as well. On the left-hand side, I've kind of plotted just a subset of 100 of the true positions, just doing a subset to like aid visualization of it. And then I've also colored them just by the Y coordinate. So when we simulated our adjacency matrix, we were using a kernel that we picked ourselves. It's kind of a translation invariant COS kernel. And so the reason for a translation invariant one is that we knew what that relationship would be. And we knew that therefore those distances in M would be proportional to the distances in Z. And then we also know, because of the dimension of the kernel, what dimension we should spectrally embed into, which was great. So the kernel was rank 5. So we should spectrally embed into 5 dimensions. And I've shown the first 3 in figure B. And in figure B, it's quite clear that we have this two-dimensional manifold. It's quite curved, looks a bit like a bar stool. And we know that the distances like along that should be proportional to the ones on the left-hand side, which we can just find and calculate and show. So it's very clear that this relationship is proportional on the left-hand side, but it's also equally clear that if we just took those like Euclidean distances, ignoring the manifold, that we don't get that same relationship. And then finally, for this one, we can show that as we increase the number of points, this recovery is just going to get better. So we have that consistency. We can see that, like, once we've applied ISOMAP, we can then align them, and we can see that when we have n is 100, our recovery is not great. And that's because when you're doing ISOMAP, you need to pick this epsilon parameter that creates your neighborhood graph. And if you don't have enough points, you end up having to pick epsilon quite large, and it doesn't really capture that manifold structure. So if we go back to this bar stool shape, if you only had 100 points on here and you needed to connect them all, you probably wouldn't be able to kind of capture this gap in it, so you wouldn't get that behavior of going around the manifold. But as you increase the number of points, that's going to get better and better, and your distances are going to get more accurate, and then your recovery is going to get better. So as we talked about before, there's kind of many different techniques to do both of these steps. And we kind of looked at a few of them just to see experimentally what they showed us. And they kind of supported the main aim of the paper, which is to say do matrix factorization and then a nonlinear dimension reduction. So you can see here that using, for example, ISOMAP or UMAP or T-SNE are all quite effective. But say again, if you did NotiVec into 2 dimensions, you're not recovering anything great. And then finally, I'm going to go through a just quick real data example that we looked at. So we looked at how the structural changes kind of a global flight network that was like during the beginning of COVID. So we had this data where each node in the graph was an airport, and 2 are connected if there was at least 1 flight recorded between them. So we had about 10,000 airports over the space of a few months, and we took the adjacency matrix and we spectrally embedded it into 10 dimensions, and then used something called degree correction, which I realized we haven't talked about, and then applied ISOMAP to that. And so what we saw was this. So with figure A, we just have the first 2 dimensions of the spectral embedding for January 2020. So you can kind of see this kind of like ray structure again. But if you then apply ISOMAP, you can see much more of the structure of what you would expect. So these are colored according to the continent. And we have like January, February, March, and April. And you can see kind of North America and the different continents and how they're structured is recovered fairly well. And also you can see that when you get to April 2020, loads of countries decided to stop having flights. So the structure changed quite dramatically there. But also, if you just focus on North America, you can see very well how it does with capturing the longitude of these places. So on the left-hand side, we have the spectral embedding and ISOmap, but restricted to North America. And the color in it kind of indicates the longitude. And we can see that that recovers the longitude quite well. The latitude, however, is not greatly captured doing this. But you can see that there's that kind of the true geography of doing this is recovered. So the conclusion of like this paper was that if you have what you believe is this latent position model, what you should do is matrix factorization into a high dimension, and then you should use a nonlinear dimension reduction to bring that down. And we can use that to kind of estimate the true positions of these objects. And importantly, you don't need to assume much about your edge generating process F. So yeah, thanks so much for coming. If anyone's got any questions.
Thank you so much. That was so beautifully clear. And I'm sure anyone who's actually looked at the mathematical content of that's hiding under this will be doubly impressed by how you were able to take something so deep and represent it so clearly. So thank you so much. Right, questions from the audience? Well, I'll kick off whilst you're thinking. The process of running this two-stage analysis, how fickle is that? Like how much tuning do you have to do to get it to work smoothly?
There are quite a lot of kind of parameters in there that aren't, there's not always very clear ways of choosing them. So for example, what dimension you should embed into. You can use like a scree plot and stuff, same with when you kind of use your dimension reduction. And also a big one for ISOmap is that hyperparameter epsilon. So choosing that can have a massive impact on your data. And sometimes if your data is quite spread out, it's going to be really hard to capture all that information. And what you could do is kind of get rid of some nodes if they're too far away. But yeah, some of those hyperparameters can have quite a big effect. But using stuff like UMAP and TCD is kind of has less detrimental, I would say, impact of that.
I see. So we've had two questions from the audience. Siddharth, do you want to turn on your mic and ask a question?
Sure. So I had a very naive question, but so in addition to the fact that these geodesic distances are recovered, is it also possible to reconstruct the kernel that generated the random graph model? Like to figure out what the function f is and to see whether it's associative or disassociative, right? In the sense of like, is it a similarity kind of graph model or is it a dissimilarity sort of graph model? So this is the question that I had.
Shall I take this one, Annie?
Yeah.
So thanks for that. Very pertinent question. So I think we believe it should be possible, and I think it's like a really interesting thing that what we haven't done basically. I think the version of your question that I think we're most likely to think about next is could we at least test, like, you know, if you give me a proposed kernel, I should know what the manifold should look like. and then I've got this point cloud, and I can ask the question: does that point cloud, is that consistent with the manifold that is implied by that kernel? Right, and I could construct a hypothesis test, and that could be kind of interesting, right? It could be kind of fun. I mean, literally learning the kernel. I mean, of course, there's plenty of work doing that. You know, not even spectral techniques, right? But that seems like a very, very valid goal. But I don't know that we exactly know how we do that yet.
I think the other problem as well is because even though there are like the classes of like families that we would probably be able to say that makes sense with that kernel, there could be other families out there that could have the same relationships. So that might be a problem as well.
Yeah, I mean, you might have to use more than just distances. You might have to somehow look at the whole shape of a manifold. But I think you definitely have to. So it'd be interesting but difficult.
Great, thank you.
So the next question's from Brendan, whose mic's not working, sorry to doubt. Can you bound the number of low dimensional components? The Hausdorff dimension is stable under countable unions, so you could possibly have one component per observation.
That's one I think I need a bit of clarification about. Can you bound the number of low-dimensional components? So I think we sort of have as a starting point that our latent position model is operating on a compact set, which typically is just comprises one single connected components. So when we only had what I would call sort of my result, basically everything up to what Annie described, there was no way of, there was no way of somehow describing how many connected components you might have in the image, that because we just didn't understand the map phi at any sufficiently rigorous level. But one of the points which might be included in a theorem Annie showed, or maybe we just decided to remove it, but one of the points actually of a last paper that Annie just described is that we actually prove that phi is a homeomorphism. So the image will have precisely as many components as their supporting set has. And in fact, topologically speaking, by phi being a homeomorphism, the image and the pre-image will be identical. So I don't know if that answers your question, Brendan, but if it doesn't, then email me or maybe write something else in the chat.
Great. Thanks very much. Okay, Wahab, you've got a question. You can just turn your mic on and ask it. Or shall I ask it? Okay, fair enough. What if you have a data set with constraints, for instance, with hierarchical constraints, going back to the school example, if the students can speak to the teacher but not the principal? So would you aim to learn these constraints from the data or include them in your embedding?
Well, one of the things we've been thinking about actually in the context of this sort of dynamic graph embedding, it is literally hierarchical structure, right? I mean, can we somehow recover hierarchical structure? And I mean, and the question is just as valid in a single graph, right? I mean, you don't need a dynamic element to ask, can I recover hierarchy somehow in the connectivity structure of a graph, right? So we have had a little look at trying to do that, and there's kind of quite interesting results about what happens if you've got like a hierarchical graph, so somehow you can group your nodes into ever more granular communities. And this sort of hierarchy is somehow dynamically evolving over time. Like, what would you expect to see in this dynamic embedding? And it's kind of beautiful. We have a sort of picture where basically the only things that change are things that are somehow above you in the hierarchy or something like that. So it's something we've been investigating, but basically the problem with that whole enterprise is that it seems to be sort of computationally difficult, statistically and computationally difficult to estimate hierarchy in these point clouds. And this is a well-known problem in, you know, in a much larger context than just graph analysis. People who care about genetics and things like that know very well, but it's very difficult to find these sort of tree structures given just relational information. So we'd like to do what you're suggesting, but it seems difficult.
Great. So I have one last question about the example that you gave where there were multiple types of graph. So I wondered whether you were using multi-edges or whether you're using multiple edges that replicate multiple times when you have a complex entity like a business transaction that links a business, but also maybe a location and multiple types of object.
And that might be for you, Annie.
Is this the corruption stuff?
It
So
is.
So yeah, with the different kinds of edges, we ended up actually looking at kind of the structural stuff and the behavioral stuff differently, because we ended up deciding that they're telling you quite different things. So the structural stuff, and there was some issues with how different their densities were as well. So with this structural stuff, it was a lot sparser. But that stuff was probably better at telling you the type of corruption where companies are owned by the same kind of people, but their ownership thing is a bit complex, or they're posing as different companies, but for some they're sharing some details in the structural side. So that side was quite interesting to tell you that. And then we looked at the activity stuff separately and did that in the multipartite way that Patrick was talking about later. And that was more to look at companies that were colluding to corrupt the bidding process itself. So we kind of split up those into two main headers of links and then use them to detect kind of different types of corruption, and then use the multipartite structure so for each of those. And then we also included some weighting as well in how important those relationships were.
Right. So there's a lot of technical details hiding under the surface. Great. Okay. Well, I think it just remains to thank you once again for that really excellent talk. And we will see you all at the next seminar. Thank you very much.
Thank you.
Thank you.